Welcome. In this video, I am focusing on the solution to a problem that was given me in the comments on one of my videos by one of my subscribers. So this problem that you see on the board was in one of the comments on one of my videos on asynchronous sequential circuits. And today we're going to focus on how we would go about finding the solution to this problem. First of all, we have to take the words and we have to put them into a diagram. So each circle in the diagram represents a total state. That is the state of the two inputs and the output. The arrows that connect the circles indicate the manner in which we may go from one total state to the next. The fundamental mode of operation of an asynchronous circuit means that because there is no clock, we change from one state to the next by changing only one input at a time. So if you look at the circle 0, 0, 0, you see we may only go to one of two states. Either we're going to change x1, in which case we will move to the state 0, 1, 0, or we may change x2, in which case we will move to the state 0, 0, 1. As you continue to follow these arcs around the diagram, you will see that every single state has an arrow going to two other states. Every single state has an arrow branching away from it. So for example, look at state 1, 1, 1. We may go to 0, 0, 1, or we may go to 1, 1, 0. Now, in the case of 0, 0, 1, we have changed x1 to a 0, which has caused a change in the output from 1 to 0, as indicated in the words of the problem itself. If we go from 1, 1, 1 to 1, 1, 0, we have changed x2 to 0, but there has been no change in the output. If you study the diagram, you will see that there are only 6 circles, and we would be looking for 8 circles because there are 8 possible states if we have 3 things. 3 binary bits will give us 8 states. It turns out that the additional states are invalid. The arcs that I have marked with the red arrows are the way we actually go around our total state diagram to actually produce the conditions specified in the word problem above. So study the worded problem and then examine the arcs marked with the red arrows to see if you can realize the significance of them. Suffice it to say that where the red arcs are marked, there is always a change in the output from 1 to 0 or 0 to 1. So you could say that the significance of those red X's on the arcs is because the output is changing as that on that particular arc. The two invalid states are 1, 0, 0 and 1, 0, 1, which, according to the worded problem, violates the conditions of the device we're trying to build. You can check that for yourself. If you have trouble understanding this part of it, please go and watch my design procedure for asynchronous sequential circuits part 1. The next thing that we want to do is to actually label the states and create a primitive flow table, as you can see there on the right. The primitive flow table has one stable state per row, and it also indicates the manner in which we may move from that stable state to the next state. So the contents of the primitive flow table completely correspond to what is shown on your total state diagram. Okay, now we're ready to take our primitive flow table and put it onto an implication table to find out how we may reduce or combine the rows. And once we do this, we will find that some rows completely go and others have dependencies. So for example, row AC would obviously depend on DF. But if we look at DF, we see that DF is a no-go. DF has an X in it. Why is D and F not compatible? Because in the last column of D and F, the output is different. In row D, the output is a 1, and in row F, the output is a 0. Rows cannot be compatible if the output is different. So both D and F and C and E are incompatible. So because of that, all the dependencies are going to be incompatible as well. So we take now the compatible squares. As you can see, there are only 4 that have ticks, and we put them onto a merger diagram. And our merger diagram shows that there are no geometric forms, so we cannot really combine any more than 2 states. So therefore, our compatibles are going to be AB, BC, DE, and FA, and those rows we may merge. So we have drawn now those on the left. We are merging A and B, B and C, D and E, and A and F. So when we merge those, we see that they're perfectly easily able to be merged. And when we do that, we can redraw that table to replace A and B with just A. So wherever you see A and B in the first row, we're going to write A. So in square 1, we would have A0. In square 2, we would have A0, as you see here when we do it. So if you compare the 2 tables carefully, you will see that we have reduced our merger. We've merged and we've ended up with A, B, C, and D only. We've relabeled our 4 rows A, B, C, and D. The next thing we have to look at is how to implement this on a transition table. How to implement it on a transition table. And to do that, we need to draw a transition diagram. Now, the transition diagram contains, by reason of arrows, the way we move between the rows A, B, C, and D. So if you study it carefully, or you go back and watch my other videos, you will figure out how these transition diagrams relate to your flow table. The problem with this transition diagram is that it has diagonals. If it was a pure rectangle, we could in fact build the circuit quite easily using 2 flip-flops. But the presence of the diagonals in the rectangle tell us that in fact we are going to need to add an additional flip-flop to make a race-free state assignment. We will continue this in another video, but I intend to carry this to an actual circuit where I can demonstrate that it actually implements what we stated it was supposed to do in the worded question at the beginning. And the reason why I find it necessary to do this is because another viewer on one of my videos said that I was completely wrong and he could easily prove it. So I came back to him and I said, go right ahead, prove me wrong. I have not received a response up to now. It does not mean that there may not be 1 or 2 mistakes in my video, since I don't claim to be perfect. But when the man told me that I was wrong, I checked the video carefully and found no errors. So if the man thinks I am wrong, then it is his job to show me where I am wrong. Otherwise, shut up. Now, the thing about it is, I don't believe that it's a bad idea for people to say I'm wrong, because even if he thinks I'm wrong and I'm not, and he shows me what's in his mind, why he thinks I'm wrong, then I can teach him. I can make another video. I can actually reveal where his thinking has gone wrong. So, by all means, I encourage people, if you think you have found an error or you don't understand, then show me what you think, and then I will either admit to an error and correct it, or I will teach you where you have gone wrong in your thinking. We are all here to learn, both you and me. Okay? So, thanks for watching, and see you in the next video.